Hello, welcome back to the first course in general physics and to the second part of thermodynamics. In this lecture, we will continue talking about thermodynamic systems and the relation between heat and temperature. We will continue from the last lecture where we talk about the heat capacity and specific heat, and we then come to discuss the heat of transformation of a system. After that, we move to another topic of the discussion of heat and work and the relation between heat and work. And then hopefully we will have time to arrive at the first law of thermodynamics. Now, in the previous lecture, we have discussed the concept of heat capacity, and we defined the heat capacity, capital C, for a body in terms of the heat absorbed by the object as it interacts with the environment and as its temperature changes from T initial to T final. The units of heat capacity is as given by the formula simply energy per degree, because Q has units of energy and delta T has units of degree or per Kelvin. So energy per degree centigrade or energy per Kelvin is the units of heat capacity. So that would be either calorie per degree centigrade if we adopt the traditional unit for heat, which is the calorie, or we use calorie per Kelvin using the Kelvin scale instead of the centigrade scale, and those two units are exactly the same in amount. And the third unit, which conforms with the international system of units, is the joule per Kelvin, and this is the international system. This is the unit in the international system, according to the international system. The name heat capacity for this quantity, capital C, could be misleading somehow in different ways. The name capacity could involve the meaning of containing something, because when we say that a pot has a capacity of this many liters of liquid, then we can put that much liquid into the pot, and thus the pot contains the liquid. However, the object does not contain heat, so the name is misleading in this sense. Also, the capacity as a name could involve the concept of the ability to absorb heat. So when we say this is the capacity, which means the limit of being able to absorb anymore. However, this is also misleading because an object can absorb heat and its temperature grows indefinitely. The temperature is open from above, as we mentioned. So there is no limit to the amount of heat that an object can absorb. Thus, the name capacity, heat capacity, somehow could be misleading, and we have to be careful with this name when we deal with this quantity, capital C, and we have to use the definition of it according to the equation that gives the relation between the heat absorbed, the amount of heat absorbed by the object, and the change in its temperature. That is this concept of heat capacity. There is another concept which is related to the concept of heat capacity. This is the specific heat. If we talk about the heat capacity of a body, then the bigger the body is, the bigger its capacity is. Because, for example, a body of iron will have a given heat capacity. That means it requires a quantity of heat Q to raise the temperature of that body of iron 1 degree, for example. And if we obtain a bigger object of iron, of the same material, iron, but a bigger object, then that bigger object will require more heat Q to raise the temperature of that body 1 degree, the same amount of temperature, by the same difference in temperature. If the heat required is higher for raising the new body's temperature, the same difference in temperature, delta T equals 1, for example, indicates that the heat capacity of the bigger body is bigger than the heat capacity of the smaller body. Thus, the concept heat capacity is not really useful when we want to talk about the properties of matter. We cannot talk about the properties of iron in terms of heat capacity, but we can talk about it in terms of another concept which is related to it, which is specific heat. Specific heat of a given object is simply the heat capacity per unit mass of that object, and that could be taken as a property of the matter that we are dealing with, because if we define the specific heat of iron, for example, as being the heat capacity or the amount of heat required to raise a unit of mass of iron 1 degree Kelvin, then that property is a property of the matter itself. Thus, when we speak of heat capacity, we speak of heat capacity of a body, which involves how massive it is, how big it is, or how small. But when we talk about specific heat, we are involved with the concept of specific heat per unit mass, which is a property of the material itself. And thus, speaking of specific heat, we are speaking of the specific heat of material rather than specific heat of the body, because that body is defined to have the unit mass. That is this concept, and this concept is related to the heat exchange between an object and its environment in the following sense. If an object of mass m interacts with the environment and exchanges heat with the environment, if it absorbs in the meantime heat Q, and in the meantime, as a consequence of this absorption of heat, the temperature of the body rises or changes. It might drop, it might rise from T initial to T final. Then the relation between the heat absorbed and the temperature change of the object is given by this equation. Q is equal to m times small c, which is the specific heat, times delta T, Tf minus Ti. C is small c is the specific heat of the body that we are dealing with, and m is its mass. Thus, m times small c times the specific heat is the heat capacity that we have defined in the previous equation. Thus, now we can talk about the properties of materials, and we can talk about specific heat of material. And as an example, the specific heat of water is accordingly dependent on the definition, is simply small c, specific heat of water, is equal to 1 calorie per gram per degree centigrade, or per Kelvin, of course, because the degree centigrade is the same as the Kelvin, but this is the traditional unit of the specific heat. And this comes from the definition of the calorie, as we noticed previously, that it is the heat required to raise the temperature of 1 gram of water by 1 degree centigrade, between 14.5 and 15.5. From this, and coupling this definition with the equation that relates the heat absorbed and the change in temperature, we arrive at this definition of the specific heat of water, which is 1 calorie per gram per degree centigrade. And that is also equal to 1 British thermal unit, BTU, per pound per degree Fahrenheit. That also comes from the definition of the BTU. Now, if we adopt the international unit, the unit of heat in the international system, and the unit of temperature and the unit of mass in the international system, the unit of heat is the joule, which is, as we mentioned previously, simply 4.186 joule per calorie. And the units of mass is kilogram, and the unit of temperature is Kelvin. And thus, converting these traditional units into the units in the international system putting instead of calorie 4.186 and putting instead of gram 10 to the minus 3 kilogram, and putting instead of centigrade Kelvin, because the centigrade is equal to the Kelvin as a unit of the temperature, then we have 4,186 joule per kilogram per Kelvin. That is the specific heat of water, 4,186. And approximately, we write it as a good number, 4,190 joule per kilogram Kelvin. That is the specific heat of water. And now we talk about the heat of transformation as the object interacts with the environment. Then it might go through a phase change or a state change as it absorbs heat, as it exchanges heat with the environment. This phase change could happen to the object that interacts with the environment and exchanges heat without changing its temperature. If a body exchanges heat with the environment and changes its state without changing the temperature, then we call this heat as the heat of transformation. The amount of heat required per unit mass for transforming the matter from a phase to another, for example, from solid to liquid or from liquid to gas, this phase transformation, the heat required per unit mass to accomplish this phase transformation is called the heat of transformation, and we symbolize it by capital L, the latent heat or the heat of transformation. This is L is the heat required to transform a unit mass of material from one phase to another, as we mentioned, solid, liquid, or gas, from one phase to another. The total heat transferred to change the object completely from one phase to another, if the object has mass m, is thus Q is equal to L, the heat of transformation per unit mass, times the mass. That will give us the total amount of heat required to transform the body of mass m from one phase to another. The heat of transformation can be categorized into two types. One type is the heat of vaporization, L sub V. And that heat of vaporization, as the name indicates, is the amount of heat that is required to transform one unit mass of a material from the liquid state to the gaseous state, that is when it evaporates, or vice versa. If the amount of a unit mass of matter condenses from the vapor state or from the gaseous state to the liquid state at the same temperature, no temperature change, that amount of heat needed for the condensation is also the same, L sub V. That is the heat of vaporization. We have another transformation process, which is the so-called the fusion, the heat of fusion, L sub F. And that is the amount of heat that is required to transform a unit mass of a solid, of a given material, to liquid without changing the temperature, without increasing or decreasing the temperature. The amount of heat required to do the reverse process is also the same. If we take a unit mass of material in the liquid state and we solidify it at the same temperature, then we obtain heat from the material. The material loses heat to the environment given by L sub F. That is also the heat of solidification. Those are the two types of heats of transformation that we can be dealing with as we are heating or cooling down a given body of a given material. So, for example, if we consider a block of ice at minus 10 degrees centigrade, which is at 263 Kelvin, at minus 10 degrees centigrade, and we start heating that block of ice, then the temperature of the block of ice increases without the ice melting from minus 10 until the ice reaches a temperature of 0. During that time, the block of ice absorbs heat to increase its temperature from minus 10 to 0 degrees centigrade, which is the temperature of melting of ice. At that point, when we have ice at 0 degrees centigrade, then ice starts melting as we add heat to the block of ice. Then ice starts melting, and it becomes a mixture of water and ice at 0 degrees centigrade, and it keeps melting until all the ice has melted. At that point, we have water at 0 degrees centigrade. The amount of heat that the block of ice absorbs in order to melt is the mass of the ice times L sub F for water. And the temperature in the beginning, before the melting process, and by the end of the melting process is 0. The temperature is the same. And then after 0 temperature, after we have reached the state of water at 0 temperature, if we keep adding heat to the system, then the temperature of water starts rising. Add more heat, it reaches a state of boiling. The water starts boiling. At 100 degrees centigrade, the water starts boiling if it is pure water. After that, the water starts evaporating changing from the liquid state into the gaseous state. And it keeps evaporating until it disappears completely as liquid, and it is transformed completely into vapor. The amount of heat required to evaporate all the water from water at 100 degrees centigrade to steam at 100 degrees centigrade, that amount of heat is equal to the mass of the water that we started with times the heat of vaporization, L, the heat of transformation of liquid to gaseous state of water. That is an example to illustrate what happens as we add heat to a system. And the heats of transformation of water, as an example, the heat of vaporization, L sub V, is equal 539 calories per gram. Each gram of water needs 539 calories to evaporate at the same temperature of 100, which is the evaporation, 100 degrees centigrade, which is the temperature of evaporation of the water, or boiling point. And in the international system of units, this is equal to 2,256 kilojoule per kilogram. Just multiply the calorie by 4.186 in order to convert it into joule, and then we substitute the gram by 10 to the minus 3, and we get this quantity. The heat of fusion of water is given by L sub F equals 79.5 calorie per gram, or in the international system 333 kilojoule per kilogram. That is obtained by the conversion of the units into the international units of system of units. At this point, we will start discussing another concept, which is the relation between heat and work. If we consider a cylinder containing a gas with a container having lead shot, full of lead shot, and we are doing this in order to be able to change the weight on top of the piston, which is closing the gas in the cylinder. And we assume that there is no frictional effects as the piston moves up and down in the cylinder, and thus if we remove few lead shots from the container, we decrease the load on top of the piston, and thus the gas will push the piston upward. The gas will expand, and in expanding it will do work, and it will supply work to the environment. For example, the work done in this case is lifting the box of lead shot upward. Similarly, if we add lead shot to the box, then we increase the weight on top of the piston, and that way the piston will go down, decreasing the volume of the gas, and that means the environment will do work on the system, or the work done by the system on the environment is negative in that sense. So we can do this, and the cylinder is stationed, the cylinder of the gas is stationed on a base with a controllable temperature, that we can control the temperature as we do any sort of process. So we can control having a process of doing work with energy absorption as heat, or without energy absorption as heat, as we wish, by controlling the weight on the piston and the temperature on the base of the gas cylinder, which is in intimate contact with the gas, and thus controlling the knob of the temperature will control the temperature of the gas itself. And this is a gas confined in a cylinder with a movable piston, and this could be an example of a machine that can exchange both work and heat with the surrounding environment. A thermodynamic process, let's define this concept, thermodynamic process. A thermodynamic process is a process by which, or through which, a system changes its state from an initial state characterized by the pressure P sub I and the volume V sub I and the temperature T sub I, to a final state characterized by temperature P sub F, volume sub F, and T sub F. This process through which the system changes from the initial state to the final state is called a thermodynamic process. Notice that we spoke about the initial state and the final state, and each one of them we characterized them by the pressure, volume, and temperature. Those parameters are intrinsic properties of the state, and thus if we define the temperature, volume, and pressure of a system, that means we define the state of the system. These are state parameters, intrinsic properties of the material, that is. During a process, a thermodynamic process, heat might be added or transferred to the system, in which case the heat is taken as positive, or heat might be transferred from the system outside to the environment, and in which case Q, or the heat, is considered negative. During the process also, during the thermodynamic process, as we explained in the case of the moving piston in the cylinder of the gas, in our example, work is done by the system, and if the work is done to raise the piston, that means our system does positive work, and the work is considered positive. It does positive work to the environment. It delivers positive work. And in the case of lowering the piston and the reduction of the volume of the gas, the work done is negative because the system did not actually deliver work to the environment. The environment delivered work to the system, and in that case we consider that the sign of the work is negative. The infinitesimal work done by the system is defined as previously in the treatment of mechanical systems and mechanical energies with a simple modification. Previously in the mechanical systems, we mentioned that the work done, the infinitesimal work done as the force is applied to a system during its displacement, a distance delta x, is simply dw is equal to f dx. If we rewrote f in terms of the pressure times the area, then we get dw is equal to the pressure times the area times dx. dx is the displacement moved by the piston, up or down. So, but the area of the piston or the cylinder times dx is simply dv. It's the change in the volume of the gas. Thus, the work done as the piston rises or lowers and as the volume of the gas changes by dv is given by dw equals the pressure of the gas times the change in its volume dv, its infinitesimal change in volume dv. That is the definition of the work done by the system as it interacts with the environment. The total work done is obtained by integrating this formula, and if we have a PV curve, meaning if we know the transition of the curve of transition of the system from the initial state to the final state, and we know the PV relation, then we can integrate this PDV through knowledge of the PV relation. If we know the track on the PV curve, then we can integrate this and obtain the work done by the system by simple integration. When the system changes from an initial state to a final state, as we mentioned, the work W done by the system and the heat Q absorbed by the system, both are in general path dependent. They depend on which path did we take in shifting or in changing the state of the system from the initial state to the final state. That is, they depend on how we changed the state, by which track, what path did we follow. Both quantities, W and Q, do have different values as we change the path of taking the system from the initial state to the final state. And we have examples here. For example, suppose the system has an initial state I and a final state F. If the system is taken from initial state to the final state, and this curve with the arrow shows the path of the transition from I to F on the PV curve. PV curve is the pressure, is the relation between pressure and volume. If this is the path taken between the initial state and the final state, then the integral of P dV, which is the work, is simply the area under the curve. That is the value of the integral P dV, because now we know a relation between P and V. And that area, which is the work, is positive because the P, the pressure, is positive, and dV, the change in volume, is also positive. So the multiplication of the two quantities will give a positive value. And this area represents the work done. Now, if we think of changing the state of the system from the initial state to the final state, but following another track, say if we change the system from the initial state I to an intermediate state A at constant pressure, and then change the state from A to state F, lowering the pressure at constant volume, this will give us the amount of work, which is again the area under the curve, and which is positive again, because from I to A we have this area under the curve, which is a positive work, and from A to F the work done is 0. Simply there is no area under this curve, which is AF. So this area is the work done, which is also greater than 0. But we notice that the work done in this process IAF is larger than the work done by the system during the previous process, the process in example A. We have another example that if we take the system from an initial state at constant volume and lower the pressure to a given final pressure, and then take the system to the final state at constant pressure, changing its volume, expanding it at constant volume, we will get also this work done, which is the area under the curve, which is also a positive work, but it is smaller than the work achieved in the previous two cases. Thus, we realize that we can change the work delivered from the system to the environment. We can change it as we wish by changing the path that we follow, and IGHF is one path where we obtain a large amount of work, while ICDF is where we obtain a smaller amount of work. And if we reverse the process and go from F to I, for example, the reverse process will give the same amount of work done in the forward process, but the work is negative in this case because dV is negative. And if we take a loop where we take the system from an initial state to a final state and then back to the initial state, then the area enclosed in the loop is the work done during that process. And at this point, I would like to finish this lecture, and I thank you for your attention.